Hi, my name is Steve Schwartz, and I'm thrilled to be moving my research over to PSI. For those of you who were able to watch my seminar a few weeks ago on CubeSat design engineering, this will be a fairly different discussion, but still with the common thread of my interest in numerical simulation of granular materials in low gravity environments. Okay, so in this talk, I'm going to be explaining my role as a participating scientist on the DART mission. For those of you who aren't yet familiar with NASA's DART mission, I'll provide a brief motivation and I'll explain the concept. So DART is a kinetic impact NEO, near Earth object deflection test, testing our ability to deflect a hazardous asteroid off of a trajectory that might otherwise have it on a path toward Earth. DART stands for Double Asteroid Redirection Test. And the double is because it's impacting a binary system, the Didymos binary system, namely the smaller component, the secondary of the binary system. The primary is called Didymos, and the secondary, which is the target of the mission for impact, has been named Dimorphos. Okay, so on this next slide, here's a plot of all objects that have hit the Earth over the past few decades, the past 33 years, since apparently tax filing deadline for 1987. And these are just objects. The objects that are shown are just those above 100 tons of TNT equivalent. And that's plotted over a map of the globe. And the red dot that you see is the relatively recent Chelyabinsk meteor of 2013, for which there happens to be multiple car dashboard videos of the event. You could find that on YouTube. And then on the next slide, this is the frequency of asteroid impacts by size. It also shows the estimated number of NEAs at that size and the percentage of those that we've located. So 160 meters across is just about the size of the asteroid Dimorphos, which is the target of DART. And it's estimated that this size asteroid hits the Earth once every 10,000 years or so. Okay, and the next slide, the next plot on this plot on this slide, it's estimating effectively the least aggressive, I guess you could say, mitigation technique, given an asteroid's size and lead time we have until Earth impact. And you can see that for Dimorphos, you can go to the next slide and it'll show up. We're clearly in the range of the kinetic impactor, which is probably the most aggressive mitigation technique that we should be testing. Of course, that's, I guess, in my own opinion. Anyway, so next slide, you can see that, so DART, the slated launch is very soon. The window actually opens in just a few months, and the impact will it'll occur just over a year from now. So it's all happening very soon, especially in terms of planetary timescales and planetary mission timescales. And so next slide, this is the kind of a schematic of the concept. So this would be you could imagine the original orbit of the binary. And then the next slide shows what we intend to do when we impact it, and we impact it, try to impact it head on, and it'll decay its orbit and it'll come into a new orbit. And this is what we're going to try to detect. Okay, and the next slide, these are the level 1 requirements. The first one is to impact Didymos. So hopefully that occurs. That's fairly important to the success of the mission. And the next one is to be able to, with that impact, change the binary orbital period and cause at least 73-second change in the orbital period, which is currently around 12 hours. and then be able to measure that period to within 10% of the targeted minimum change in orbit, which is 7.3 seconds. And that's from ground-based observations. And then the fourth one is to be able to then characterize the momentum enhancement factor, which basically comes from the model of well, it comes from what kind of ejecta is produced. So depending on the target, you'll get different ejecta, and the ejecta that comes, and if it goes, in the opposite direction of the impact, that enhances the momentum that's transferred to the asteroid. And here's like a kind of quick visualization. It's not exactly accurate, but the next slide, this shows this beta, which is the momentum enhancement factor. Basically, what you can take from this is that the higher that it is, the more ejecta has been spit out behind you, and the more momentum enhancement you give to the asteroid that you're trying to deflect. And the next slide shows some, very preliminary models of different types of targets and what kind of ejecta they produce, and therefore what the momentum enhancement factor would be. Okay, in order to characterize the evolution of the ejecta, the next slide, what has been done so far by the group and by myself in past years has been to use this kind of a classical sort of idealized scaling relationship proposed by Hausen and Holzapfel from many of their papers. This kind of gives the formula of that, but basically, without describing all the parameters here, feel free to ask me, but that gives you the initial conditions of the ejecta, and then you put that into an n-body code, and you watch it launch, and you characterize where all the ejecta goes in the system, in the Didymos system. And we get that from experiments. So the next slide shows some measurements of various experiments to characterize some of these scaling laws. Again, I won't go into detail, but you can ask me questions about it. So this is what has been done in sort of the easiest way to characterize the ejecta. And the basic strategy here you can see from the next slide, is we take a local frame that has ejecta coming out from an impact, and we put that into the frame of the Didymos system in the gravitational environment, including solar radiation effects and so on, and tides as necessary. And then we let it propagate in the system. So that's sort of how it looks. And so what I'm doing is, you can look at the next slide, is I'm trying to basically bridge the gap from the impact working group to the ejecta working group. So the impact working group is performing lots of hydrodynamic models and stuff of the cratering event, the impact and the cratering event, using hydrocodes, various hydrocodes. And so what I'm going to be trying to do is move that to an n-body code. So right now, it's that has not been attempted because it's difficult for many reasons. One reason is, and we consider the impact speed of almost 7 kilometers per second, and we're talking about ejecta. The relevant ejecta goes down to a little below the escape speed of dimorphos of the body, which is on the scale of tens of, or not even less than, maybe less than tens of 10 centimeters per second. So that's 5 or 6 orders of magnitude, and that's quite difficult to bridge because that's down into the numerical noise if you're looking at if you don't have the right resolution. So it's a careful process. So that's kind of my that is my task as a participating scientist on the mission. And I've had I'll just mention next slide. I've done some work on this in the past. So I've used, in order to model the fragmentation phase, I've taken from 3D smooth particle hydrodynamics code that's worked by the Benz group in Bern, Switzerland, including Martin Utzi, Eric Asfog, and we model the impacts using various strength and friction parameters, porosity, equation of state, and then model the gravitational phase. Next slide. Using PKD-grav, which is a parallel n-body tree code to model the gravity and the collisions. And the next slide gives sort of an overview of some of the, some or most of the frictional forces to date, which again, I won't go through in detail, but you can ask me. But the point is that it's suitable for modeling granular dynamics and the evolution of the ejecta in this case. And I've done some of this before a couple of years ago, studying the disruption of calculating the catastrophic disruption of comets and whether or not they can lead to bilobate comets like 67P. And yeah, next slide. And we've had some success in this area. So the cratering is a bit tougher of a challenge, but I think I am up to it. So with that, next slide, I'll just leave you with the contact model in the numerical code, and I will take any questions. Thank you.